Disruptors and curious minds, CEOs, founders, book lovers, we're back. I'm Mark. This is Jeremy. And you're listening to the Thinking on Paper book club, where we explore the insight, the strategies, the ideas, and sometimes the downright lunacy of books that will change your mind, books that have stood the test of time, books like The Nexus by Julio Tino, Thinking on Paper.xyz. We read that. Check it out.
One of my favorites.
Books like The Design of Everyday Things by Don Norman, a classic of the design genre. Thinking on Paper.xyz. Check it out.
Don Norman was a guest, by the way, on a full 1 hour show. Yes.
Books like Clear Thinking by Shane Parrish, who hasn't been on the show yet, but we learned about clear thinking strategies, what matters and when it matters, perhaps more importantly.
Everybody knows
on
Shane
paper.
Parrish.
Yeah, .xyz. Ideas are bouncing around the world on satellites at the speed of light, but we're joined by the oldest technology of all. And because it's quantum season on Thinking on Paper, we have a new book, and it's all about quantum computing. It's called Quantum Supremacy. It's by Michio Kaku, who some of you probably know. And yeah, it's a new book for us. So I'm going to pass the baton over to Jeremy to introduce it for us. Welcome back, Jeremy, by the way. How's your summer been? Good?
Summer's been great. Yeah, thank you. And this book is off to a great start. Just as how we got to this book, I saw Michio Kaku talk at a conference, like a Future Forward conference, like 6 years ago or something like that. Okay. And he's a theoretical physicist, teaches he's a professor at some college in New York. I don't have it in front of me, but teaches physics, teaches quantum mechanics, is one of the kind of involved in the author of one of the authors of string theory or contributors to string theory. But he had me when he was on stage and he said, Jeremy, he didn't say Jeremy, but he was talking to the audience.
He was talking
he
to
said
you.
Jeremy, but I hear him say Jeremy in my head. Hey, guess what? We're not going to have to worry about building these spaceships and these rocket ships that can go past the speed of light, because we're going to be able to send our consciousness beamed across these little beacons across the universe and get there near instantaneously. And I was like, holy crap, dude. Okay.
When they're doing that, when we're beaming our consciousness to orbitals in the far reaches of the Oort cloud, will we still be reading books? Because wouldn't that be amazing?
Well, you think about it, all consciousness is, well, there's a lot to it, but like the physical nature of consciousness is electrical signals in your brain. So it like does make sense, right? A little bit. But anyway, that's what got us here. But quantum season is why we're here, right?
Yes.
So chapter 1, we're gonna be really ambitious in this episode, and we're gonna try and get through 4 chapters. Holy smokes!
Part 1.
The good news is these 4 chapters are relatively introductory, but there's a lot of really cool stuff in here. So the first chapter talks about it's the end of the age of silicon. All right. So talking about the general transition from classical compute to quantum computing. And again, we all know there hasn't been demonstrable success of what quantum computing can do, but it's coming. Like we all know it's coming. The ability of this technology is there. It's rooted in the basics of physics, of quantum mechanics, right? So
well, what I liked is, so the part what it kind of tells us how we got here from the birth of computing to where we are now with quantum computing. And Michio has this nice skill of dropping these absurd numbers into proceedings very early on, where for example, the Chinese Academy of Science went even further. They claimed their quantum computer was 100 trillion times faster than an ordinary supercomputer. So like laying out what the potential of these machines could be. It's quite mind-boggling.
Agreed. And this one quote captured my mind in a really interesting way, talking about traditional computers. And this is a theme that we'll start to learn more and more as we read the book. But traditional computers can't really simulate chemical reactions. It can't really simulate nature, right? It's just not in their nature to simulate nature, right? So listen to this. Traditional computers, too crude to describe the delicate waves of electrons dancing deep inside a molecule. So, he puts a lot of big facts and figures, but like Carlo Rovelli, he sprinkles in these like really interesting, that's kind of cool. Dancing electrons, delicate waves. Like, it's a pretty thoughtful thing. But what his idea is that quantum may actually be able to simulate the chemical processes, the biological processes, these super complex things that happen in our body, because quantum is more natural than traditional computing, right? Traditional computing, as we'll go into, is this one and this zero, and these combinations of ones and zeros, these ons and offs allow us to process information, right?
Yeah,
But
like a classical computer is something that kind of we have created out of something that didn't exist before, whereas quantum computing is really channeling the very fabric, the building blocks, if you like, of the universe and everything in it. So it's much more natural than a classical computer.
yeah, and if you're not believers in the fact that quantum is coming, or it's en route, or it's being heavily worked on, in 2021, the US funded $625 million toward quantum, supervised by the Department of Energy, which, interestingly enough, all of these like newer technologies end up getting folded into the Department of Energy for one reason or another. Um, and some of the things that jump out to me too in this is like he starts thinking about, all right, well, what is this stuff potentially going to be good for? So we talked about the modeling, the simulation of complex chemical and biological things, right? He had one of these things that quantum could actually help us potentially find a super battery, like a battery that's so good, and so, I guess, long lasting, and not caustic to the environment, maybe, not causing fires in cars, maybe. By modeling these reactions, by modeling these chemical reactions, we may be able to come up with a new battery. And I think batteries, like, that's a pretty big solve if that's the case, right?
Yeah, yeah. The battery. He seemed to be quite adamant that the solving the battery conundrum was a big use case of quantum, a practical one. I mean, he mentions search optimization, simulation, data analysis, quantum medicine. He says quantum will feed the planet. All of these kind of cures for our ills. But yeah, the battery one, and that's because we're bad at creating batteries because we can't simulate the chemical reactions that we need. Is that correct? And the quantum computers will be able to do that to such a degree that will literally save billions of hours and get there much quicker.
That's what I got out of it too. And then a couple other things he points to, the Haber-Bosch process, right? That bacteria does something, that could potentially be applied to the Haber-Bosch process, which is what generates fertilizer. It did a lot of other things, but it helps us make fertilizer to grow food and that sort of thing. But this process takes 2% of the world's energy, which is like, holy smokes, right? But bacteria actually does something for free at no power cost, similar to the Haber-Bosch process, that we don't fully understand and we can't fully harness, because we don't have the compute to simulate what that bacteria does and what it could do in other states. So I think that is another interesting thing. Could we find an efficient way to make a better fertilizer for cheaper and less power cost and less caustic to the world?
I think that caustic's a good word. I think a lot of the underlying systems which support our world are quite crass in that
Hmm.
they're almost like they've been bodged together to create something. And yes, they work, and yes, they're kind of efficient, but they're a bit crass. And quantum computing will allow us to just create very, very optimized, almost perfected versions of what exists before, and create new ways to solve the problems that these cranky, crass solutions solve.
Great words, man. Great words.
Yeah, I think.
Cranky and crass at the same time. The third thing that he pointed out, as a potential thing to point quantum at, is what they call the protein folding problem, right? So you have,
Okay.
proteins in our body, are these little starting points for, how to make things in our body, right? How to make, ourselves, arms, legs, the whole organs, all of that stuff. But there's a company called AlphaFold that he referenced that mapped structures of 350,000 proteins, right? So they've mapped individually these proteins. I don't think they use quantum to necessarily map those, but they did. But to make any good use of that giant catalog of mapped proteins, you have to have a style of computing that is more relatable to organic processes, right? And quantum is more able, or in theory, more able to do magical things with data and information like that. So who knows what the heck will come out of that? But it was really interesting to see him point to actual things. I'm like, yeah, I guess that does make sense, because remember, the tie-in is that quantum is more natural than classical computing. And then we can model more natural things like that.
Well, the kind of the subtitle of the book is Unlock the Mysteries of Science and Address Humanity's Biggest Challenges. And so, this isn't about solving for the simple things. This is about solving for the big things. So why would the listeners want to read this book? So from the opening part is, so it gives the reader a history of computing from Babbage all the way to today. It talks about quantum mechanics, quantum physics. So we see the same names that we've spoken about in book club, that we've spoken about with other quantum seasons, Godel, Alan Turing, Enigma, Lovelace, Max Planck. Max Planck was, the more I read about Max Planck, the more I think that guy was he the smartest guy that's ever lived? Like, some of the things you read about him and what he came up with, even his mind seemed to be working on a different level, even to Einstein, didn't it?
Well, he was the catalyst for a lot of this. You had Max Planck, and then I'm not sure how you actually say this name. Someone's going to butcher me in the comments, but de Broglie, or is it Brogle, was another scientist, and then that flies into Schrodinger, and that flies into Einstein and Max Born, and there's like this whole path of because science builds on science, right? But let's that was a good cast on why someone will want to read this book. It starts on where we are, what the potential of this great technology could end up doing for us, and then showing how the digital age came together too. So let's run through that. Chapter 2, the end of the digital age, talked about Babbage, right? Babbage talked about, is mathematics complete? I could spend a lot of time just thinking about this. Like, he was like, because a lot of people thought math could solve everything. Like, there, but he started thinking about,
Debunked.
he started thinking about, are there true statements not provable by mathematics? And that was like, whoa, like, no, math is supposed to do all the stuff. And like, how do we do it? And then knock, knock, Godel walks in. He's like, yo, there's a thing called an incompleteness theorem. And, math doesn't solve anything because of a lot of other different things. And I did try to read Gödel Escher Bach, which is a book that compares Gödel's work with MC Escher's work and with Johann Sebastian Bach's work. I got about halfway through it and it like broke my face. I might go back to it, but anyway, this end of the digital age talks about Alan Turing, who was probably one of the greatest minds in the history of humanity with what he did, with basically creating this. All right, we're going to have an infinitely long tape, and they're going to be squares, and in the squares you can put a 1 or a 0 in it, right? And the processor reads the tape, and it could do a number of things. And I thought this was really interesting how it lines it out. You can read the number in the square, you can write the number in the square, you can move it 1 square to the left, you can move it 1 square to the right, you can change the number in the square, and you can stop. That's the start of like the initial process of computing. And I was like, wow, that was really interesting to read through that, because I didn't really understand. I understand what Alan Turing did and the things that he did during the war and the Turing test and all the wonderful stuff that he did. But like, to really look at it and have Michio Kaku say it so succinctly in like 6 or 8 lines, I was like, man, that's pretty cool, man.
Yeah, and just a note on his tragic demise, Alan Turing, as well. That was a disaster. And
well, yeah, what thanks did he? So he basically, there's data supported, but it's all estimated, that Turing's work actually shortened the war by 2 years and saved 14 million lives. And
Yeah.
what did they end up doing? They ended up putting him into chemical castration or whatever, else happened because they found out that he was gay. It was
Yeah.
like, what in the hell kind of reward is that? How are we? I mean, how backwards? I mean, we could spend hours just talking about the bullshit that is. But anyway, on to
But
more.
on but on the when he was explaining that the tape and the 1 and the 0 and okay, ones and zeros, you can have this, you can have that, and you can go left and it can go right. I had trouble visualizing how you go from that to me speaking to you, beaming this around the world, and it's essentially using the same principles as that tape with ones and infinite zeros on it, and it was yeah, I couldn't bridge that. It
Well,
was too hard for my brain.
it's like looking at the Sumerian cuneiform tablet, seeing the marks in the clay, and then reading a book and going, "Holy shit, how did this all come together?" But
Yeah.
it's all a catalyst and it's all a start.
There's a lot of smart people out there.
So
Could
here's
I just read
please.
a little bit of light on the Godel and the whether mathematics is complete and when he proved that it wasn't. Shockwaves rippled through the mathematics community. 2,000 years of Greek thinking was completely and irrevocably shattered. Mathematicians around the world were left shaking their heads in utter disbelief. I like that.
Yeah, yeah. It's again, I like it. I like his writing a lot. And if you've
Yeah.
ever heard him talk, he's got a very there's a little bit of quirkiness to him, but there's a little bit of like this matter of factness coupled with like a willingness to like jab a little bit. And it's kind of cool. I almost hear him talking when I'm reading his book. So the bridge from chapter 2 to chapter 3, check this out. Turing's work is, and this isn't a quote, this is kind of me capturing an idea, but as I read, Turing's work is based on determinism, right? Which means that when you feed a question into a Turing machine, a computer, you get the same answer every time. It's predictable. Guess what? Quantum basically flipped the script on determinism, right? And they talk about that kind of going into chapter 3, which is essentially like, what is quantum, right? What are we talking about, and how did it come about? Talking about Planck's constant, that is like the actual measurement of the smallest thing that you can measure, 6.62 times 10 to the negative 34 joules per second, or H, right?
Yep.
So I know I'm rambling, but I want to get this out of my head real quick. So there was an interesting analogy with like Planck's constant and like a radio dial. And as Planck's constant is 0 or less, we move into the world of like us and what we see, right? And which is what we learn from color Ravelli, all an approximation. But as we turn the dial to increase H, then the quantum world becomes more visible. So imagine if like you had a Max Planck machine that had a dial and you could just go and you would actually start to witness quantum situations. It's not possible, but like theoretically, it's interesting to think about. That's how we explain Planck's constant.
Is that connected to the idea of the wall? I can't remember who it was. He
John
quoted that
Wheeler. Yeah.
John von Neumann,
Oh, von Neumann. Yeah.
and the war between the micro and the macro, and there's this. There has to be this place where it changes between the quantum realm and the classical realm, and scientists of the day said no, it has to be gradual. He says there has to be a wall, and does that in the same as your radio dial where you tune it in to tune into the quantum, you're kind of crossing that wall from the macro to the micro to the
Yeah, von
quantum
Neumann
realm?
also talked about moving the wall, right? So when you're talking about an equation or talking about a situation, you actually move the wall one way or the other to incorporate the data that you want to incorporate. So yeah, I think it's totally in there. Well, then it talks about. Do you know how to pronounce Debrogle? Is it de Broglie or de Broglie?
What page?
This is somewhere in chapter 3. He's a scientist that basically, had the idea of like, if light was a wave and a particle both, this duality, nature of light, then why not matter, right? So it was his idea that to consider like maybe electrons could have the same properties as photons and could be both a wave and a particle. And that was the handoff to Schrodinger, where he came up with the wave equation for electrons. And then, that kind of, got pushed along to Max Born, who was thinking of matter as particles, but the probability of finding that particle is given by a wave. So it's always interesting. I think he did a great job of like summarizing just from a high level. This isn't a quantum physics book, but it laid the waypoints of the journey of quantum.
Well, could you explain superposition and entanglement in a concise way for our listeners then, Jeremy?
Probably not.
Um,
Probably not. Well, so entanglement, as I understand it, is kind of the nature of like why we can get more processing out of quantum computers than we can out of traditional computers, because these qubits, these quantum bits, are entangled. They're paired together, vibrating at the same frequency. They're like soulmates, right? They're soulmates, right? And when they're entangled, they can actually have the ability to be literally in two, kind of two places. Superposition is the two places at once, right? So the ability to transmit information between those entangled bits is kind of what allows this new capability. At least as
yeah,
I understand it.
yeah, regardless of where they are, that it could be one could be the other side of the galaxy, and they're entangled, so they can transmit data. I've got a question for you because there's something I really didn't understand
Yeah.
in this, and so it's on page 56, and they're talking about entanglement, and they're talking about superposition, and Einstein claimed that nothing can go faster than the speed of light, as this was in violation of special relativity. So okay, if two electrons are communicating over the vast darkness of space instantaneously, then the data is moving faster than the speed of light. That's impossible. And that was his part of the why he was trying to debunk, or didn't really believe, that God doesn't play dice with the universe. The quantum, there's something wrong with the quantum theory. It doesn't work for him. And then he's, but then essentially this idea of entanglement is proved to be precise and accurate, and it does happen.
Well, if you
But Einstein had, I'm going to quote here, but does this mean that information can travel faster than light, violating special relativity? Einstein has the last laugh here. No. Although the information that traveled between the two electrons was instantaneously transmitted, it was also random information and hence useless. This means you cannot send useful codes containing a message faster than light. If you analyze the signal, you only find gibberish. So you can move gibberish faster than the speed of light, but you can't move tangible information. But what does it matter if it's gibberish? I couldn't understand what was the importance of it being gibberish, because it's still
let's
moving faster than the speed of light.
let's talk about that, right? So there's
Please.
a little footnote in figure 5 that that talks about but this doesn't violate relativity since the information that breaks the light barrier is random.
Yes,
So I
but it's
start
still
thinking
breaking the barrier.
So I start thinking about that. So imagine there's another reference. He another thought experiment. And he talks about. He's like, man, every time I walk across my carpet, I think about all of the other versions of me that are walking across in every single infinite possible path across this carpet,
Yeah.
including the path to Mars and back. Right, is going to be one of those paths. So think about all of these different paths. But in order for one thing to happen, the wave function has to collapse. Right. So maybe you have two particles and you have gibberish going between them faster than the speed of light. You still have to have the wave collapse to make that gibberish into anything important. So the speed of light, eventually the bottleneck eventually becomes that we have to collapse the waveform in order to make the gibberish useful information. I don't know.
So,
PS
so
guys, hey, listen, this is very important. I'm not a computer scientist. I'm not a quantum physicist. I'm a curious mind trying to figure this out in real time. It takes a little bit of vulnerability. So go easy in the comments, but please comment. Go ahead, keep going.
is this the, until it's measured, or it's till it's interacted with, the wave function is it's a probability. It's Schrodinger's cat is both alive and dead, and until you interact with it and the waveform collapses, all states are possible. So is that gibberish being transmitted, and until you interact with the wave function and it collapses in on itself and reality becomes what it is that gibberish is actually just a probability. It's not really it's not
Maybe.
really happening, and until you interact with the waveform and it becomes reality. Therefore, it also almost a speculation of something moving faster, gibberish moving faster than the speed of light. But until you interact with it, it can't. And when you interact with it, it's not no longer gibberish. Therefore, nothing can move faster than the speed of light.
Quantum physicists,
I had
quantum
no
computer
idea.
scientists, come join us. We'll put you on a box on the screen. You can help us make sense of the fun stuff that we're reading. Although we enjoy kind of walking around it and trying to figure it out ourselves as well. So as we think about the craziness of quantum theory, he references this in a couple of places in the first 4 chapters. The quantum theory is one of the most successful theories of all time, meaning that the proof behind it is better than most scientific theories out there, which I thought was pretty interesting. Like the math behind it, and was so it was the most successful, meaning like there was the most proof behind it mathematically to prove that it's there, even though we can't see it.
Okay.
There's a great summary of quantum mechanics in general on page 48 for those of us reading along. It's a nice little bulleted list. I thought that was really cool. Let's move into chapter 4.
Is that the dawn of quantum
The
computers?
dawn of quantum computers.
Well, my favorite part in chapter 4, obviously, is the parallel universes in your bedroom, the multiverse theory.
I love that.
It's always the best. So he uses your radio signal. So basically, the idea is that for superposition and this probability of existence to work at the quantum level, it has to work. It works on a universal level. So therefore, there are an infinite number of universes all going along their own paths in parallel to ours, but we can't see them, we can't interact with them. He uses the analogy of a radio again, whereby if you're sitting in your living room listening to the radio, there's hundreds and hundreds of signals coming into your radio, but you're only listening to whatever channel you're listening to because you're only tuned into that one station. So even though all the other signals are there, you can't listen to them. And they explain that the multiverse theory could work in a similar way. All these universes are happening, but you're not attuned to them. So there's a dinosaur next to me right here, but
Yeah,
we never cross.
I love it, man. Vibes are real. Like vibes are real. It's not just a hippie in the mountain town, living on a homestead talking about vibes. Like vibes are real. Like I don't know if you've ever studied cymatics, right? It's what sound
No.
does to particles, and there's
Okay.
certain so there are these sensors that are flat sensors that vibrate at certain frequencies, right? You could make them vibrate at frequencies, and those frequencies are just like musical notes, right? Like 440 hertz is I think, is it an A? I want to say A440, on the musical scale, but you can actually vibrate frequencies, and you put sand on the top of these platters and they vibrate at certain frequencies, and they make very specific shapes
Right.
out of the sand, like that look like snowflakes. And it's the same damn snowflake every time that it vibrates at a certain frequency, right?
Oh, it
So
never creates a different snow. So it's always the same picture out of the sand.
if
A
based on a
particular.
frequency, right?
Yeah.
Based on a frequency, right?
Wow.
So the idea of like things in this room right here, there's other shit, maybe there's other shit happening, but my radio antenna is not in tune with that vibration, and I am what's called decohered from it, or my
Yes.
coherence with it is not there. It's the decoherence is the challenge, right? Um
I think
so
there's a nice segue on page 79 about that, because very often if you talk about multiverse and parallel universes, some people will just switch off. But then there's a quote here, David Deutsch, I don't know who he was exactly. But David Deutsch takes these mind-boggling concepts seriously. Why are quantum computers so powerful, he asks? Because the electrons are simultaneously calculating in parallel universes. They are interacting and interfering with each other via entanglement. So they can quickly outrace a traditional computer that computes in only one universe. And that was quite a good way to imagine why it's so quickly, rather than thinking about ones and zeros and this probability of between 1 and 0, and it's all of these different infinite functions at one time. If you imagine it, and it's easy to imagine parallel universes next to you going on forever, and if those electrons are just entangled between all of those solving these problems, then you can kind of visualize it a bit better, I thought.
Yeah, it's kind of like, yeah, we're not gonna spin up a VM, like a virtual machine, or we're not gonna spin up an Amazon processing instance, compute instance in the cloud. In the future, we're gonna spin up, you know, two electrons and, have them, be coherent and process on them, right? That's what we'll do. We'll have a factory that'll just spin up, hey, Mark, you need to do some processing. We'll spin up a couple of electrons. We'll entangle them for you, and you can do all kinds of shit. And that'll be Mark's entangled pair to do your processing on. Pro tip. There's your business idea, guys.
I'm waiting for the internet built on lasers. I want to see light particle. I want to see data. I want to see my data engraved on a light particle and sent to you. I want this podcast to be engraved on light and sent to you, because you tell me how the hell does that work? But they speak about it.
I'm still baffled just at the silicon process in
Yeah,
general on how that works, and how,
yeah,
it's etched in with UV light, and you pour acid on it and it carves it out, and you
yeah.
can fit a billion of them on your fingernail, and it's like, that is freaking mind-boggling alone when you think about it. But like, man, where is
Well,
this stuff?
that's the end of the, like, Moore's law can't go on forever, can it? We can't just keep shrinking down these transistors to that they're already at the atom level. At some point you can't go any smaller. But leading into chapter 5 on the race is on, then in chapter 5 we get to learn about that not all quantum computers are built equally, are they,
Was
Jeremy?
I supposed to read chapter 5 or just chapter 4?
Chapter 5, chapter 4. I read chapter 5, and I
You
tell you, it's a
you you
banger.
you went ahead. So I stopped off at chapter 4.
Okay, that
So
sounds good to
let's
me.
let's save chapter 5. But another thing that I noticed, it was a theme in all of the chapters here, was like, man, if we could just figure out how the hell nature does quantum without needing to control the environment, right? So nature does quantum photosynthesis.
Tunneling, Jeremy,
Yeah.
tunneling.
So photosynthesis is a quantum process, but do
Yeah,
you see trees like having to be sequestered in this sub-zero Kelvin box that, makes them do that thing, right? So like, quantum can help develop quantum, right? So if we can model the process through quantum computing, that is a natural quantum process, that will in turn help us figure out how nature does quantum without having to be at 0 Kelvin.
a question for you then, because I could understand the how nature does it via tunneling. That the tunneling aspect of it made sense to me. Just to quote, when faced with a large energy barrier, normally a particle fails to penetrate it, but in quantum mechanics there is a small but finite probability that you can tunnel or penetrate through the barrier, and this might be why complex chemical reactions of life can proceed at room temperature. Why, and this might be a stupid question, but I'm bringing my stupid card. Why
I got
is
a pile of them behind me.
does he say photosynthesis? He uses the example of photosynthesis. Why is that a quantum reaction? Why is photosynthesis an example of nature performing quantum mechanics? I
It's a,
didn't.
it's a great question that I don't have the answer to, but could be an awesome follow-up that we can research. I don't recall the exact details of it, but he referenced it a bunch of times.
Yes,
Mhm.
and like the processes involved in photosynthesis are taking place at the quantum level. Although like everything's taking place at the quantum level, Isn't it?
I'm looking. Let's see. Well, yeah. In other words, photosynthesis violates the laws of Newton. Let's see. Hold on. I've actually got
You
it
just
right
imagine
here.
someone back in Newton's time, just like as Newton's trying to outlay his laws of the universe, and some heckler at the back is just going, "Photosynthesis violates your laws, Newton."
Yeah, we saw earlier that quantum computers have to be kept at near absolute zero, but Mother Nature can perform marvelous quantum reactions at room temperatures, such as photosynthesis and the fixing of nitrogen for fertilizers. Under classical physics, there's so much noise and jostling of atoms at room temperature that many chemical processes should be impossible under these conditions. But somehow Mother Nature has solved the problem of decoherence.
Okay.
More to come on that, guys. More to come on that. Let's see. What else do we want to? How do we want to finish wrap? At the end of chapter 4, he kind of starts leaning in on the idea that quantum can break encryption and Shor's algorithm, trapdoor functions. But the note that I got from this was, it's still going to take a long time for a quantum computer to crack encryption, but the time it will take to do it with a quantum computer is slightly more tolerable than the time it would take in traditional computing. So it's a time thing. Like, can we wait? Are we patient enough to wait, 4.6 years for this, encryption to break using normal computing, or are we okay with waiting 2.4 years in quantum? It's not like all of a sudden,
2.4 seconds.
yeah, it's not like quantum's, yeah, right. But so we talked
I
about
guess
that.
it
They
depends how
go,
much money is at the other end of the encryption.
that's right. That's
Excuse my
right.
cynical mind.
Laser internet. Talk to me about that. We'll talk about laser internet and QKD to finish the chapter. Talk to me about laser internet.
Laser internet is what I was saying earlier. I want to engrave this podcast onto a light particle and send it around the world. And I want someone to explain to me how you can can do that. In the future, top secret messages may be sent on a separate internet channel carried by laser beams, not electrical cables. Laser beams are polarized, meaning that the waves vibrate in only one plane. When a criminal, okay, doesn't that? It's before that, but
Doesn't really go into that. He just teases the possibility of it.
Well, I was listening to something the other day. It might have been this, it might have been something else, but they're talking about using light, like putting information on light particles.
Wow.
Which I think is kind of the laser internet.
Well, lasers power networking right now, right? So, like, if you have a building that has an incoming, wide area network connection coming in from a network provider that comes in on a wavelength that's basically shot across the electrical equipment on a piece of fiber, like on a piece of glass, and that wavelength, that signal goes down the wavelength, and that's kind of how I think he's talking in this case, that it's like a steady stream beam going from one place to another, and if you try to tap into that beam, the polarization is offset, and then it's like, hey, something's going on with the connection, let's lock it down. I don't know.
Okay. Mate, yeah, I'm talking about something completely different. Yeah.
If you
I,
know
I
about
like
laser,
engraving data onto light particles sounds more out there.
if you know about laser internet and you know how to engrave information on a light particle and send it across the world, please comment. And because Mark and I would love to have you on the show, and we can try to understand how the hell that can happen.
Is that me who's dropped off the face? See, the light particles have dropped. Old-fashioned tech. Usually it's Jeremy's internet that breaks. Anyway, so if I'm still recording, Quantum Supremacy. The first part of the book outlines how we got here. What is a quantum computer? When we break into the next part, it's going to tell us what we can do with those quantum computers once we've made them. So without further ado, that's it. Jeremy's gone. This is live broadcasting at its finest. If I was on the radio and I just let there be static dead air, I would have been fired. Anyway, that's Thinking on Paper. That's Book Club. Join us next week where we'll be going deeper into the quantum realm. And in the meantime, I'm going to be emailing and messaging Mr. Kaku himself to get him on to explain some of these concepts. Because as you can hear, we're amateurs. We don't even know what we're talking about, but we have fun doing it. So stay disruptive, stay curious, keep thinking on paper.